In this chapter, we're going to explore acids and bases. And we'll see that this is a very much equilibrium central topic. And in the next chapter as well, we'll also be talking about acids and bases in the context of buffers and titrations. But for right now, we'll focus on the easier aspects of equilibrium in context of acids and bases. First things first, though, we're going to want to define what an acid and a base are, right? So historically, there are a few definitions that we can use when looking at acids or bases. And I'm just going to set this up now. Typically, we focus on acids. This is just what chemists typically do. Bases behave much the same way and exactly the opposite. And all of our focus is going to be on the acids, but the concepts are true for bases just from the other point of view. And so we're going to first take a look at definitions, and then we'll see how these two are related to each other. So, Arrhenius, one of our favorite chemists, right? The one who did all those kinetics laws. Who also did some density stuff. I'm sure you hate him. But he provided a definition for an acid and for a base that we kind of use in Introchem a little bit, and maybe a little bit when we're talking about naming compounds. But we don't really use it in terms of chemistry. So Arrhenius's definition was an acid was a substance that produces, substances that produce H plus in solution. And if we think about how we learned naming rules, when we learned how to name compounds, we had a category for acids. And all of those acids started with H. And as we know, they were paired with anions. So we have H plus as part of those compounds. And so if we take our favorite acid, say hydrochloric acid, we see that in solution, of course, it's a strong electron. It breaks apart. We produce H plus and Cl minus. Or if you want to be a little bit more correct about it, it's technically HCl combining with a water molecule or multiple water molecules to form H3O plus, plus the chloride ion. Or instead of H3O plus, sometimes we have more complex structures. Like if we have 3 water molecules that are holding that proton, we can have other things. But typically H3O plus is fine. And just as chemists, H3O plus is a more kind of physically accurate representation of what's happening with an acid. Acids will form H3O plus in solution. That's a bit more accurate because we don't really see H plus ever floating by itself. It is just a proton, right? A hydrogen atom is a proton and an electron. Generally speaking, most isotopes of hydrogen, right, are or the predominant form of hydrogen is the isotope that has no neutrons. So H plus is essentially a proton. We don't see subatomic particles just floating around by themselves. Not something we typically see. Just like we don't really see electrons by themselves either. They're just going to other things. So technically, H plus is not really accurate. So H3O plus is, but we're lazy chemists, or rather focusing on convenience, we can say. So typically we write H plus, but really we mean H3O plus. So for this class, of course, I will be using H plus because I am a lazy chemist. So I'm sorry, I mean a convenient chemist, right? So I'll be using H plus, but really understand that it's really H3O plus would be the species we're looking at. So acids produce H plus in solution. We see hydrochloric acid here as a reactant dissociating or reacting with water, take your pick, to form H plus. And so it's an acid. By contrast, a base is the same thing, but it produces OH minus in solution. And so we have one of our favorite bases, NaOH, sodium hydroxide. When that dissolves in water, we can even, well, this is dissociated right now. We break that apart into its ions. Lo and behold, there's our OH minus. When we look at how this would react with water, this is technically going to produce a water molecule plus an OH minus plus a sodium ion. It's super not obvious for us right now, but we'll see how that comes into play in our next kind of category of acids. So notice again, we end up with the following. And as you probably can tell, since this is a molecular equation, we can just probably get rid of those H2Os anyway. But chemically speaking, technically, that water is, we're consuming a water molecule, producing a different water molecule. So go figure. But the point is, again, we have that OH minus. And while it may be super easy to see with something like NaOH, other things that may not obviously have an NaOH can produce OH minus as well. For example, if we put ammonia with water, we see that it produces the ammonium ion and hydroxide. So ammonia is a base as well. It's able to produce hydroxide in solution. And, it may not be obvious, right? We see ammonia, okay, well, there's no OH on it. Where is this OH coming from? It's actually the water. The water is going to be producing the OH minus. The ammonia is actually just going to be taking a proton away from water. And if you think about it that way, we arrive at our next definition, which is the definition we're going to use throughout this course, which is the Bronsted-Lowry definition. And I believe we have a line through that O for the Swedish name? I don't know. With this, we're going to kind of broaden that definition. So the problem with the Arrhenius definition is we limit acids and bases to their behavior in water. But we're going to see, especially if you take organic chemistry, that acids and bases can definitely still exist outside of the context of water. And so we don't have to worry about solution. So we're not constrained to that anymore. We're going to actually look at behavior of molecules instead of just their ability to produce something in water. And we're going to see that acids will donate a proton to a base, whatever that happens to be. And so we're going to categorize acids as something in terms of chemistry, actual chemical reactions. Acids will give a proton to a base, to something else. Right? So if we consider HCl plus water forming the hydronium and the chloride, we see here, if we take a look at the following, our products here, we can kind of make comparisons. We can say, okay, well, this H3O plus thing, where did that come from? Well, let's look on the reactant side. What's the most similar? Is H3O plus more similar to HCl or to H2O? Hopefully we can see it's more similar to H2O. And when we're considering what's happened here, if we look at H2O to H3O plus, the only difference is that we have gained an H plus. And by contrast, if you look at Cl minus, which of the reactants is more similar to Cl minus? Well, that's the HCl, right? We see for this one has lost a proton, right? We have just gotten rid of one of its protons. It's the only proton, but we'll see with polyprotic acids we'll have multiple sometimes. But the point is here, HCl has lost a proton, meaning it's donated that proton to something else. So we'll call HCl the acid. By contrast, the water has gained a proton. It has accepted a proton. And we're going to see that, therefore, our definition of base will be the substance that receives the proton. So bases accept protons from acids. So your acid will donate, it will give away a proton to your base. your base will accept the new proton. And if we're just looking over the course of a reaction, your bases will gain protons, and your acids will lose protons over the course of a reaction. So we can identify them by looking at what's happening in a chemical reaction. And so we can do the same thing with the ammonia. We saw that this made NH4 plus and OH minus, the ammonium hydroxide. And we remember in our chemical reactions that really the H3 or NH3 kind of bubbles away, but for the purposes of this equilibrium, we can see what's happening here. Well, we want to look at the products. What is most similar in the reactants? Well, hopefully if we look at the NH4 plus, we can see that that's most similar to the NH3, and we can see that it has gained a proton. Therefore, that's the base. This is our base here. And thankfully, because we really only need to figure out one thing, once we know the base, we know the acid, right? It's the other one. But let's just be good about this. We see this OH minus is similar to the H2O. We see that the only difference here is this is lost H plus. Therefore, this will be our acid in this reaction. So we may not be familiar with talking about water as an acid, but it can behave as such, so we can call it an acid. So that works. And if we revisit the last one, we saw that HCl was our acid, and then water was our base. Now that's curious. Water is an acid or a base. That's weird. We'll see that in the next video. But to summarize this one, we're going to focus on the Bronsted-Lowry model of acids and bases. We're going to define acids as substances that give away a proton during a reaction, and bases as the substance that will gain a proton during the reaction. And so now that we have our definitions, in our next video we can take a look at identifying acids and bases, do some practice, and some more definitions.